secant is a line, ray, or segment that intersects a circle at 2 points. So looking at this, this is what a secant looks like here. This line here, AC, this line here, BD, those are both secants to the circle. Unlike a tangent that intersects a circle at exactly 1 point, a secant's going to go through and it's going to intersect, go through the circle, intersect again. And it creates from the points of intersection a chord inside the circle, right? When it goes through, right? But the whole secant line is the line. The point from A to C, that line segment, is just a chord. And when the two secants intersect inside the circle, and I'm going to write these words here, this is important, inside the circle. When we get done with this part of the problem, we're going to do outside the circle over here, because that's going to happen in some of your homework problems too. So we're going to look at both scenarios. So two secants can either intersect inside the circle or they can intersect outside the circle. Okay? And we're going to create rules for these properties, equations, whatever, in order to figure out missing pieces. So, what I want you to really focus on in this problem is this arc AD and this arc BC. Okay. That's what's going to end up being related to this angle 1 that we're looking at. Notice angle 1 is the same measure as the angle above it. They're vertical angles. We learned that in chapter 1. These two angles here are the same measure as well. So, and I prefer to use x instead of 1, so I'm going to put an x here. All right. So we want to see how angle x relates to other things in the picture. I don't know how that got erased, but let me put it back on there. Specifically, it's going to relate to these two things. If the angle x was here or here, it would have related to these two arcs here. So you're seeing with the angle here, these angles relate to the two arcs associated with those angles. All right? Now, to do this relationship, I'm going to do one extra thing here. And if I were writing a proof, which we haven't done that recently, but if I were writing a proof about this, one of my steps in the proof would be to draw the segment I'm about to draw. Okay, so we're going to kind of walk through the thinking process of a proof to do what we're going to do here. We're just not going to write up a formal proof about it. So if I drew AB in that segment there, it creates for me a triangle where this triangle, let's just call this point E. If we look at triangle AEB, this triangle, X is an exterior angle to the triangle, and let's call this Y and Z are remote interior angles. Okay, you might recall that terminology back from earlier chapters. We have an exterior angle to the triangle. We have two remote interior angles of the triangle. Can anybody remember the relationship between the exterior angle of a triangle versus the remote interiors? The two interior, two remote interiors, the two far away from the triangle, the angle, these two add up to that one. So I know that X equals Y plus Z. Now, looking at the picture I've drawn and focusing in on specific aspects of the picture, what I want to relate is this angle measure to these arc measures. I know that's the relationship I have to get because arcs have measures, angles have measures. Arcs have length, angles don't have length. So it has to have something to do with their measures, right, in degree form. All right? And if we take a look at arc AD to start off with, notice that arc AD right here is created by this piece AB and this piece BD, right, which form this angle Y. Can anybody relate the angle Y to the arc length AD in some way, shape, or form? Y being an inscribed angle and AD being the intercepted arc of that inscribed angle. What's the relationship between this angle and that arc? What's half? Y is half of AD, AD is twice Y, right? So this is twice Y. Using the same logic, notice this angle BAC, which we're calling Z, right? This angle here opens up to this arc BC. This angle is an inscribed angle. This is the intercepted arc. So whatever this angle is, we double it to get that arc measure. Now, the equation I created off the exterior angle formula, the exterior angle equals the sum of the remote interiors, right? It doesn't have 2y and 2z in it. It has y and z in it. So I'm going to use a little algebraic manipulation. Anytime you have any equation, if you have some object equals some object, you're allowed to add the same amount to both sides, subtract the same amount from both sides, multiply the same amount by both sides, divide the same amount by both sides. I want 2y and 2z to be in my equation over here. Do I have 2y and 2z in there? How do I make 2y out of y? No. How do I make y become 2y? Multiply by 2, right? So I want these to be 2y and 2z, so I'm going to multiply by 2. But again, in equations, if I multiply anything times 2, I've got to multiply everything times 2. So I'm going to take the entire equation here and double it. That's going to give me 2x equals 2y plus 2z. Again, I wanted my arc lengths to be in my formula. 2y is an arc length, or measure, arc measure, and 2z is an arc measure. So now 2y and 2z are in my picture, right? So now if I start replacing things with what they actually are, x is angle 1, right? So 2 times measure of angle 1 equals 2y, which is measure of arc AD, plus 2z, which is measure of arc BC, again, x, y, and z had different names. Actually, x, 2, y, and 2z had different names. So x is angle 1, measure of angle 1. So 2 is 2, x is measure of angle 1. 2y is measure of AD, and 2z is measure of BC. So I just substituted those things right in. And my task was to figure out how I can find angle 1. So if I want to find measure of angle 1, if I divide everything by 2 now, measure of angle 1 is equal to the two arcs intercepted, added together, divided by 2. That is the relationship between the angle and the two arcs when when secants intersect inside a circle. Also, if chords intersect. If these were just chords instead of secants, we'd have the same picture, right? We still have AD, BC, this angle, right? So this plus this divided by 2 makes that. If I'm inside the circle, I add the arcs, divide by 2. That's the relationship you need to get stuck inside your brain like super glue. When I'm inside the circle, the inside angle equals the sum of the arcs divided by 2. Okay. Let's take a look at outside the circle. That's over here. So this is what it looks like. First, draw a circle as pretty as you possibly can. You see my circle? Does it look pretty? Just prettier? Good, good. All right. Mine's kind of lumpy. That's fine. As long as it looks circular, you'll know it's the circle you're talking about, right? And I'm going to have two secants intersecting the circle, but I want the angle where they intersect outside the circle. So draw one line like so, and then a second line out here like so. The main idea is that you have this point of intersection outside the circle. It doesn't matter if your lines look identical to mine or not, just make sure you're not inside the circle of the intersection of the lines. Let's go ahead and name these points here. This is going to be A, this is going to be B, this is going to be C, and this is going to be D. We'll call this point E, and we'll call this angle here X. All right. Now, the rule I'm about to show you that we're going to create here also works if there's a tangent and a secant together or two tangents together. The same rule exists for all three scenarios. So it's two secants, a secant and tangent, or two tangents. If the angle formed by the intersection of these things is outside the circle, that's what we're going to create happening here. Okay. And I want to draw again, I just want to construct a line from this across or that across, doesn't matter which one you go with. I'm going to go with A to C. So just make a line AC to create some triangle. We're always making triangles here because triangles are easy to work with. Now when we look at this picture, notice the same setup as what happened over here. We have an exterior angle and two remote interior angles. We have an exterior angle. I'm going to call this one Y this time. Y is the exterior angle. X is the interior, remote interior. The other remote interior is down here. We're going to call this one here Z. Okay, so again, the angle we're looking for this time is outside the circle, so that's the one we call X. Y and Z are the other two angles. I just use X, Y, and Z, so I don't have to write measure of angle BAC. I can just write Y. It's just easier to write it out. Okay, so I'm using these variables here just to make my math a little bit easier to look at. So once again, the relationship between these three angles is always exterior all by itself equals sum of the remote interiors. So Y equals X plus Z. Okay. Y and Z are doing the same thing that Y and Z did over here. Y is intercepting an arc, Z is intercepting an arc over here. Y is intercepting an arc, Z is intercepting an arc. So this time, this arc here has to do with Z, and this arc here has to do with Y. If that's Y, BC is going to be 2Y. That's Z, so AD is going to be 2Z. Same way it did over here, right? Once again, my formula doesn't have 2Y and 2Z in it, so I'm going to double everything. So this is going to say, down here, 2Y equals 2X plus 2Z. Once again, 2Y and 2Z are measures of arcs. X is the angle we care about, right? So I'm going to get measure of BC equals 2X plus measure of AD. 2Y is measure of BC, that became this. 2Z is measure of AD, that became that. X is still X. And again, if I want to get an X formula, X equals everything else, I'm going to move the measure of AD to the left. So measure of BC minus measure of AD equals 2X. So again, I pulled the AD to the left, so it became negative. And then I'm going to divide by 2. So I end up getting X equals measure of BC minus measure of AD divided by 2. Okay, there's my formula there. So the end result of both of these facts here, when you deal with secants to a circle, if the angle happens inside the circle, we're going to add the arcs, divide by 2. If the angles intersect outside the circle, we subtract big minus small, divide by 2. The arc farther away from the angle is always bigger than the arc closer because angles open outward. This gap is smaller than that gap. Although figures are never drawn to scale, that's just a fact of math that can't be avoided. The big one farther away minus the small one closer to divided by 2 equals the angle outside. Again, if that's a secant and a secant and a tangent, or a tangent and a tangent, big arc minus small arc divided by 2. They're all the same relationship.